Welcome to the Rock Coding YouTube channel. My name is Anton, and today we're going to be talking about concurrency, parallelism, and asynchrony in Python. The reason we're touching on this topic is because if we will end up making some kind of big scraper, or we want to do a lot of scraping, we're going to be producing thousands and thousands of requests. If they're all going to be running synchronously, one after another, it is going to take a long time. So what we want to do is actually execute them concurrently, or in parallel, or asynchronously. Having these three choices, what are these three choices and which ones should we be taking? We will need to learn quite a bit of terminology for this. So first of all, let's go ahead and take a look at the code. Here we have a method that is going to do collection, and we're executing it over here. The first thing that we want to learn about are threads. So when you run your application, it is a single execution thread that is going line by line executing your code. What you can have is you can have two threads execute the same code, and then you're going to get parallelism. So that is what parallelism is, and don't worry too much about what exactly is a thread. Just think of it as if a computer was a human being, you just have two of them now, and they're both executing the same code at the same time. That is parallelism. Now, if you're executing requests in parallel, the individual worker is still going to wait for the request to finish. Concurrency in this case is saying that I, as an individual worker, when I kick off a request, I'm not gonna sit there and wait for it to finish. I'm gonna go ahead and kick off the next request, and by the time I kicked off all possible requests, then I'm gonna sit there and wait for them to finish. Once they're finished, I'm gonna do whatever other work I need to do with them. Stepping away from the code a little bit, hearing those two explanations, an analogy might help a little bit. So let's say that you're in a kitchen and you're making breakfast. If you're making breakfast in parallel, what might happen is you just have two kitchens, two people, and then two people are going to start the kettle, and then they're going to put bread in the toaster. They're going to make breakfast, right? Or what you might have is you might have a single kitchen and you have two tasks. One task goes to one human, he starts the kettle. One task goes to the second human and he starts the toaster. And then they both, like idiots, stand there and stare at the thing and wait for it to finish. This is if you have parallelism without concurrency. Concurrency means that there could be one worker, one human, that starts the kettle, doesn't wait for it to finish, goes and put the breads in the toaster, starts it, and then doesn't wait for the toaster, goes and pets the dog, or I don't know, checks his phone, and then when he hears that the kettle is finished or the toast is ready, he then comes back and resumes the task. So that's the main difference between concurrency and parallelism. Parallelism is just doing the same things at the same time. Concurrency is about not getting blocked when you're doing things that rely on external tasks. Now, when we bring in asynchrony on top of this, asynchrony just means it doesn't matter what it's going to be, parallelism or concurrency. Asynchrony is a tool that a programming language gives you, and all it is call this method or write this code, and then the language, Python, is going to figure out for you what's better. Is it better to run it in parallel? Is it better to run it concurrently? It's going to handle all the thread management, all of that. You don't need to worry. All you need to say is, I want this work performed asynchronously, and you don't care. It may be performed in parallel, it may be performed concurrently. You just don't want your application to sit there and wait for the thing to finish. Now with this, hopefully we have a little bit more of an understanding of the differences between concurrency, parallelism, and asynchrony. We can come back to this code and we can say, look, we're making one request, we're then making 5 more. We can actually perform 6 requests at the same time, and then whatever work follows can be executed after. So if we put this request in parallel and this request in parallel, how do we make sure that this work gets performed even though if this second request finishes first, right? You don't know what actually is going to be finished at what time, and this is the hard part about concurrency and parallelism, because things are happening out of turn essentially. So the first thing that we're going to focus on is parallelism. We're going to remove this function and we're going to spin up a thread. Let's go ahead, type in thread, and here we will import thread from threading. So from threading, import thread. And this is as if you're going to create a human being, a clone that is going to do work for you. You have two parameters. First is the target, which is going to do some kind of work. So let's say that this is work. And in here, we will put a while loop. That is going to look something like this. We will do the work, and then you want to say daemon true. Daemon means that it is a worker thread. A worker thread is a background thread, and all it means it's a low priority thread. So if the main application thread finishes, we do not wait for worker threads to finish. They just terminate at the same time as our application. So we create this thread, and then we're going to call the start method on it, which is going to start executing the work function. Inside of here, we may pass something like print. Let's say hello. If we run our application, we may or we may not see hello. And did we see it twice? And then we see some kind of crazy error, which is basically the work thread being terminated. As we're currently looking at this thread, it is essentially a closed box. What we want to be able to do is put work inside of it. It is going to do the work, and then we will take the results. You know, kind of like school, where you have all of the students, you give them work, they do the work, and then you collect it, and all of the work has been done in parallel. Let's say we will produce 30 works, so in range from 0 to 30, and in here we want to push work into the thread. The way that you do the pushing is generally through queues, and I'm going to take a second here to highlight queues. Queues are important. When you start building bigger systems and you have multiple servers communicating with each other, it's not much different from multiple threads communicating with each other. You will decouple them using queues. So while I have your attention, make sure that if you have cloud credit, Azure, AWS, Google Cloud, doesn't matter. Look up what the message queue service is. Go ahead, spin up an instance, and make sure that you know how to interact with it. It is going to be pivotal to your career. Now, let's continue. We are going to say queue equals queue, and we will take queue from queue. All right, so from queue, import queue. Make sure call parentheses to execute the constructor and create a queue object. The queue object will have a put function where we will be able to put something into it. So this can be a number. We know we can pass around functions, just like we can do variables. So we can actually put a function in there at some point. When the worker is doing the work, it can then go to the queue and get the work. This is going to be some kind of number, and we can actually print it out. So working on, let's say, n. This will have to be a formatted string. And then once the work has been completed, we have to go onto the queue and call the task done function. This means that whatever item we got here, we have finished processing it. If I scroll down a little bit at the bottom, what I'm going to do is I'm going to call join on here. Join is basically going to say once all of the things that we have put into the queue have been completed, then resume. Otherwise, the application is actually going to hold here while the thread in the background is going to be processing these tasks. Okay. Here I will run the application. It is going to pretty much complete instantaneously. I can scroll to the top and import time, and then I will use time to delay the work that is being put onto the queue so we can see it a little bit slower. So sleep for 0.01 second. If I run this application, you can see it goes by a little bit slower. If I drop down the terminal and scroll up here, essentially two processes are happening here. First, we're putting tasks onto a queue, and then the second one, the tasks are being processed by the thread. What we can do at this point is, because we know how to create local functions, say that this is local work. We will pass the name of the worker here, and we will say who it was completed by. At the end, we will return local. And that is the actual work that is going to be happening over here. And we have to produce the local function. So we'll say that this is worker 1. We execute this, and the result of this function is going to be this local function. We can then copy this line and produce a second worker. If I bump this number up to 100, open up the terminal and run the application, we will see that the work that is being done is alternating between the two threads. If I drop down the terminal and instead of delaying how fast I put items onto the queue, and rather how long it takes to complete the task. I'm not sure what this window is. Let me remove that. And I'll say that it takes the task half a second to run. If we have a single worker and I open up the terminal, I run the application, it is going to take quite a long time. I will actually exit and we will use the time to time how long this actually takes. At this point, we're going to be putting on tasks, so perhaps we want to start timing here. On the time class, we can find the process time function, which is going to be the start. We can then copy this line, put it after join, and this is going to give us an end time. By the end of this, we can print out end minus start and essentially know how long this has took us. So I will decrease the time that we sleep for here, rerun the application, and the process time is actually pretty bad. I was meant to use performance counter. So this is going to give us the time it has taken in seconds. So rerunning this is 1 second. If I put in a second worker and rerun it, it goes by twice as quick. Now this will have a half-life, so if first one was a second, this one is half a second. If I run this is 0.4. So it doesn't mean that you can keep adding infinitely more threads and it's going to be quicker and quicker. The fact that you need to create or destroy a thread, that is actually going to take up computational resources as well. And something that you don't actually want to be doing is managing threads. You don't want to know how many threads you need, if you need to create one more or one less. This is where, instead of just having pure parallelism, and by the way, we're not getting to concurrency where this is this effective request execution, we're going to step away from that and we're going to focus on parallelism, and actually we're going to focus on asynchrony, where inside the concurrent namespace there is going to be futures, and in here we want a thread pool executor. The way we use the thread pool executor is, instead of spinning up these threads, we say with thread pool executor, and in here we say how many workers we may want to have. In this case, we'll say we will have 3 workers. We'll say that this is executor, and then we will use the executor to start scheduling work. In this case, we have to call the submit method. The thread pool executor, you can look at it as a bunch of threads together. So let's get rid of this and think of it as we've consolidated that logic into the thread pool executor. The submit logic in this case gets rid of the queues. Internally, it is going to have a queue which is going to distribute it between the threads. So this logic can go as well. The actual things that we were putting into the threads was this work right over here. We can get rid of most of the stuff here unindented, and because it is asynchrony, we essentially have no knowledge about what kind of thread is actually going to be executing the work. We can still have the number, and the way that the number is going to be passed is if we have a range from 0 to 100, so same tasks, we want to submit to the executor this work 100 times, and the I will go as a second parameter and will be passed into the send. So args and comma quargs will be passed into the underlying function. We take our start timer, we put it somewhere at the beginning, cleaning this up a little bit, opening up the terminal, rerunning the application, and we get an approximately the same result. If I drop down the terminal, at this point we essentially create 100 tasks for which we have to wait to finish, and they get finished by the end of this with scope. If we take the max workers and we remove them, what we essentially get is a way more improved result. So in the background, Python is going to automatically figure out how many threads to create and what's the most optimal thing for you. Now that we're familiar with this, we can actually remove this work that we're doing over here. We will say that we will actually create 5 tasks which are performing this do collection over here. If we run the application at this point, we will see it's running in 0.8 seconds, and that's not a very good indicator of anything, how many things have been collected, etc. Let's actually take a look. We'll create a results queue, so a new queue, and the reason I'm creating a queue and not a list is because the results queue is actually coming along with thread safety. So if multiple things write to an empty collection, there is a chance that only a single element will be written. With a queue, it is thread safe, so no matter how many threads are writing into it, the addition of elements is always going to be consistent. Here, I'm not going to be putting the whole HTML, I will just put the status code, and we are going to make sure that we're getting the correct amount of results on the queue. So if we're kicking off 5, we have 5 here. We want 25 in total. If we take the results queue on the end after we have finished, we take a look at the queue size, open up the terminal, rerun, and we should see 25. Not sure what that error is, so results queue. Okay, so this is not queue, we want queue size. Let's rerun this, and we see 25. Perfect. Now what we have over here is a request and 5 requests that follows. So a single collection journey has 6 requests. We are scheduling the whole collection journey. How about we split up this request which follows into its own task? So let's create def next. This is going to be a separate function. We'll take this work, place it into the function, and then schedule next like this. Unindent this. If we rerun the application, we're going to get more or less the same result because we've just shifted this logic along into a different function. What we want to do now is, instead of triggering this function from this function, we want to place this function onto the executor. And then the tasks that we're actually executing are going to be a lot more fine-grained. What we can do is take the executor and place the scope somewhere up here. Essentially do something along the lines of this, where we take the executor and we submit the next work right over here. Remove these parentheses, and then if I open up the terminal, run the application, we're going to see a bit of a strange issue. Essentially, the tasks which are scheduled at this point finish, and up until we actually submit the next tasks, the executor is kind of already destroyed. What we really want to say is we are big boys, and we will take the executor and we will initialize it outside of the with. We are saying that we are capable of managing this ourselves. So let's create a little bit of space. Alongside with the results queue, we're also going to have a work queue. The reason for the work queue is we have the executor, which is available globally. We start putting stuff into the executor, and this is going to start producing essentially work objects. We want to keep track of these work objects on the work queue and one by one make sure that they are finished. We're going to pick up a work item of a queue, we will wait for it to finish. It may be already finished, and through its lifetime it will produce more work items which are going to go back on the queue, meaning that at some point we will stop producing work items and the queue will be drained. So anytime we submit work to the executor, we actually want a function like submit work, where we are going to pass a function as a parameter. We're going to use this to submit the work to the executor, function like this. On the back of this, we're going to have work which is already happening. We will then take this work which is already happening and put it into the queue. The only reason we're putting it into the queue is to wait for it to finish at the end. So while a work queue empty not empty, let me scroll down, a work queue, we're gonna try to get an item, some kind of work, and on this work we will be able to get the result. When we're calling result on the work which is being put into the queue, we are waiting for that work to finish on the main thread. On the background thread inside the thread pool executor, that work is still happening. So two things are going to be happening at the same time. You can imagine that here we're taking a look at the individual kettle or toaster and we're looking at it work, and inside the thread pool executor it is actually doing the thing. Once that work has indeed finished and potentially has produced more work items for us to pick up from the queue, we have to remember that we have to say we have acknowledged that this work has been completed. So task done, Task done doesn't do anything with helping to pick an item from a queue. It just, the items that go through the queue, it finally kind of ticks them off. This has been processed, this has been processed. So if you have a join on the end, doing this is basically for safety. That's now down. Let's go ahead and rerun this. We obviously get 0 items. Let's take a look at what we have. So we have just submitted stuff into the executor without actually putting it onto the work queue. So we want to use the submit work function instead. We'll replace it here and replace it here. Open up the terminal, run the application. And here we can see that we're completing these 25 requests much faster, well, maybe not much faster, but faster than we were doing them previously. So if we had 5 journeys before with 5 requests more, if we have max workers, let's say 5, this is going to sort of peak at this 63:59 point. If we then say we want to increase the count of workers, this is going to go faster. Before, it would kind of cap at 5 threads because the most that we can process is 5 journeys. Okay, now that we are parallel execution asynchrony masters, let's go ahead and create our component for scraping. So we're going to go into our library over here. We'll take the thread pull executor with the submit work and we're going to go into run. And inside of here, we can actually create our own runner. We'll create a class. This will be a runner. We'll define a init function and put this logic over here where on this class we will create an executor. We will import the thread pull executor as well. We will be able to submit work to the runner. This is going to have a self function. So self, fn, the executor will be present on the self. And then finally, we're going to need a work queue. So let's go ahead and grab a work queue. Again, we're going to put this into the constructor, self work queue, import from queue. There are a bunch of queues. Make sure you import the right one. Again, reference the work queue via self. Before we run the scraper, let's create our runner. So runner equals runner. I'll remove the max workers. And so we can properly pass arguments to the submit work. What I'm going to do is I'm going to add asterisks, args, and quarks. On the runner, we're going to submit the work of the entry point and then args as parameter. Now we need to do something about the results. So define a new function, submit result. Again, we're going to have a self, some kind of result. This may happen in parallel, so this is going to be a results queue. We can use self results queue, put result onto the queue. Don't forget the colon on here. And I'm seeing over here, these are grayed out, so let's just make sure we pass them along over here. And now something to get the results. So get result. We don't need to submit any results over here. We're gonna have results array, by the end of which we want to return. So results, again, we will take this queue while empty not. We wanna get the individual item that we have collected, take the results and append. You can make this a lot nicer with generators, although that is a big topic to throw into this video. So we're not gonna be doing that. By the end of this, we can take the runner and get the results. What will have to happen to our scrapers under the hood is essentially they need to support this parallelism. So when we're passing parameters into the individual functions, if we take a look at BBC Foods and collect recipes over here, alongside with the search term, we actually need to be able to accept, and inside the main function, alongside the args, we need to be able to accept the runner and somehow propagate it. So keyword arguments will be really good for this. If we want to keep backwards compatibility, we can essentially pop this 2 ways. If we go to the run scraper over here, take this function, copy it, put it right over here, run scraper parallel. We now essentially want to revert the work that we have done here. So let's again take the entry point, execute it with the args. What we really want to do is run a quick check. So args -1, this is going to be last argument. And if the last argument that we supply, so last will equal something like -b, so we're just asking for this to be run in parallel. we're going to do just that. So call the function run scraper in parallel, pass scraper, and for the arguments, we're going to pass everything except the last parameter. So this will go on the args. When we go into the entry point, when we submit the work, so the very first time, what we are going to do is we're also going to pass the runner itself as a keyword argument. This is going to go inside the quargs and into the submit function. So when we go back into the main function, which is going to be executed over here, we are going to ask for a runner, which is going to be of type runner, which we can import from scraping.run. We'll then take the collector into its own variable, collector equals collect recipes, take the runner, submit work. The work will come from the collector with the start collection function and the search term as the parameter, just like that. Return doesn't really matter this much at this point. Remember that we're really just submitting items into the runner. What we can do is we can take the runner and pass it into the collect recipes, or we can make the runner append the parameter automatically. Although I will say try to manage the runner manually through dependencies in the constructor. Don't just automatically put it as a function parameter. Let's double check that this works. Scrape BBC food. Pizza. It looks like it's telling we're missing one positional argument. I think from the beginning we can say if this is none. This still doesn't count as a keyword argument. I clearly can't remember how to Python. Let's have our args and quargs. And from the quargs, we will get our runner, which is going to be the runner of type runner. Args will remove because we're already accepting some kind of positional arguments over here. Let's rerun. Let's check out what we got in the quargs over here. Maybe this method is not triggering the way I expect it to. Of course, we're not passing the parallel flag. And there we have it. So let's remove the print. This works just as expected. Let's see if this will work fine as well. Open this, rerun, and this looks to be working fine, or maybe not. Let's move this to trash. Just realized that the collected items will need to be submitted. So let's take the runner, go into collect recipes, and by the way, I did that by using F12. And here I'm gonna define the init function. I will assign the runner, self-runner equals runner. The runner will come from the constructor. Let's go ahead and import so we have our auto completion. We're going to remove the none and we're going to be submitting data through the runner now. So in main py, we're going to make sure we take the runner, put it in the constructor, and when I put things into the constructor, I like to do it this way. Just gives a clearer understanding of what is being assigned to what. If I come back to collection recipes now, I can take the self.runner, and every single item that is being submitted over here, this can actually go, the results can go. In here, we can submit result. So take the recipe, put it over there. And I think that will be it. Let's go ahead and rerun. Take a look at the output. Of course, we have nothing. Let's go into run. So this makes sense because as we're submitting work, it goes onto the work queue and we're submitting the results onto the results queue. We call get results right after we submit the initial piece of work and we have not collected anything. So we never enter the while loop, we just return the empty array. So before we actually return any of the results, we want to make sure that we have actually completed all the work. Let's take this while loop, we'll put it over here, and before we start draining the results, we want to make sure that all of the work has been drained as well. Instead of the results queue, we're going to go to the work queue, place it over here, and make sure that we are awaiting on the work. So grab the work and the individual work item. We'll then grab the result, open up the terminal, let's rerun this, take a look at the output, and there is our pizza all collected in parallel. There are no additional requests, but we can actually create those. So let's do just that. We will come back to BBC Food, and here we're gonna have pizza sauce. Go ahead, pause the video if you need to find this information. But here is essentially the link. I want to grab this pizza sauce. Accidentally moved the DOM. Let's go ahead, grab pizza sauce. I don't know how many times I've said pizza sauce, but here it goes again. So right at the top, the initial request in the preview over here, I want to search for pizza sauce, and I'm looking for the thing in the actual JSON payload that we were extracting the data from. And there it is. It should be on the URL property. And I've seen it just briefly, but it should be there. So on the recipe, let's actually collect the individual URL. Let's say maybe before the title. Go back to collect recipes, a URL. This is going to be recipe data, URL, comma. We're going to recollect, look at the output, format everything, and see if we have the URL. There is nothing here, and that is because when I've added it to the recipe, I've not added it to the item. So let's go ahead and make sure we do that. Or rerun, look at the output, and here we have the URL. So now I will just grab the whole domain. If I go into collect recipes and create essentially what is the next request, so def next request or further request, this can still have the self, and this can accept the URL. If I do have a recipe with a URL, so recipe get URL, on the self runner, I want to submit work. This is going to be next request or get further recipes. And the additional URL that is going to be supplied is this URL right here. The next work function is indeed present on the object, so I have to reference it through self. And let's add a little bit of space so it's a little bit easier to look at. I'll grab the request that is happening over here. The URL part can go somewhere over here. We'll then try to extract some simple data. So over here, one of the simplest things that you can test with is just looking for the title. If we come back here, we will take the selector, create it over here. Bada bang, take this HTML XPath. We will just go to the title straight away. We will say that this is a title. Take self runner, submit result. And here we're going to be submitting a simple dictionary where we'll have not tutle, but title pointing to title. Let's say URL pointing to URL. However, you can put in more stuff in here, right? Make sure that everything is indented properly. We'll run the application and we'll take a look at output. And here we see quite a bit of data. So our recipes end right around line 217. And the rest are individual links that we have visited. If there was information to collect there, we would have. The point here is that we're now capable of splitting our code into chunks, which has a request or may have potentially multiple requests if we care about them happening synchronously. We can define individual units of work, send it to the thread pool executor, and collect all of the results asynchronously as well. This will be it for this video. Thank you very much for watching. Hopefully you've enjoyed it and learned something new. It's very good to know about this parallelism stuff. However, same as most other things, Python has libraries and frameworks for web scrapers, which tend to handle all of this stuff for you. Nevertheless, thank you very much for watching. If you have any questions, make sure to leave them in the comments section. If you enjoyed the video, don't forget to leave a like and subscribe. If you're enjoying my work and you would like to support me, please do so on my Patreon. If you do, you also get the source code and a very big thank you from me alongside with all of the patrons that are currently supporting me already. I really appreciate your support. As always, thank you for watching and see you in the next video.